Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is: Does size really matter? Design effects on crystal downsizing. Our speaker is Sarah Moschütz. She will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during this presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the webinar control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibitions@we-online.com and we will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. Also, the recording will be available at our website shortly. But now, I will hand over to our speaker, Sarah, and I wish you an exciting presentation.
Hi everyone and welcome to this presentation today. My name is Sarah Moschütz and I'm a product manager for frequency products at the Würth Elektronik eiSos. The topic of my presentation today is: Does size really matter? Design effects on crystal downsizing. As you may know, most of the application nowadays get smaller or thinner. This means, for example, smartphone, laptops, wearables, smart home, and also sensors and multimedia in automotive application get smaller and smaller or thinner, and on the other side need more and more technical parts inside. So we need to have more parts inside the application, but we have less space. So what does normally happen? We need to have smaller parts. And that's the topic today. So if we use a smaller crystal, what effects does this have and what we need to consider during our design? I would like to show you the agenda for today's presentation. So we will start with a short introduction. Then we will move on to some crystal basics, just to have some basic information, which we then need to explain the effects on crystal downsizing. So for the introduction, it's maybe interesting for you to know that in November 2017, the Würth Elektronik eiSos acquired IQD Frequency Products. This is a company in the UK which offers frequency products for over 45 years now in the market. Since November 2018 now, we also sell frequency products in the Würth eiSos catalog. So we have over 350 crystals and oscillators, which we can offer now to you as a customer. And now in the last 2 years, we also introduced some additional new products. And by today, we have over 500 standard crystals and oscillators. IQD at the same time has over 50,000 pieces and products they can offer to you. So there are many more parts you can get. And if you have any questions about any part, you can always speak to your Würth ADM or as well contact IQD. Then we move on with some crystal basics. So what is a quartz crystal? A quartz crystal is the crystalline form of silicon dioxide. So it's just a piece of rock, you could say. So you can grow some big quartz bars, which you need for the production. And then you just cut out some small pieces, which are also called wafers. For this process, you need to have really precise angle for cutting out the blank out of the wafer. You need to have this precise cutting angle to make sure that you have the right electrical parameters. If you created this wafer or blank, you need to lap it down. So you need to make it thinner or to have a specific thickness. This is required because the frequency of the part depends on the thickness of the blank. So the thicker the blank is, the lower the frequency is. And on the other way, the thinner the blank is, the higher the frequency. This is important to know because when you think about small pieces or small size crystals, you may recognize that the size is really small. So we talk about heights of 0.6 millimeters. So the blank should not be too thick. So this means lower frequencies are not available in the really small packages, just because physically they are too thick for the small packages. This is something you always need to keep in mind. So if you want to have like 8 megahertz or 10 megahertz, this will be not possible in small SMD packages. And moreover, as you all know, smaller does not always mean it's like cheaper. At the moment, the optimal size price behavior would be at the 3.2 by 2.5 millimeter parts. They are not too thin or too small and also not too expensive. So price-wise, this would be the most interesting part for you maybe. If we would now look at the equivalent circuit of the crystal, it would look like this. So you would have a resistor which represents the damping of the mechanical oscillation because your quartz blank will have a mechanical oscillation. You will have an inductor which is representing the oscillating mass of the crystal. You will have a capacitance C1, which is a dynamic capacitance, which just represents the piezoelectric effect of the crystal. All of this will be in series, and in parallel to this, you will have a shunt capacitance, which just represents the coupling capacitance of the quartz crystals, so the blank and the electrode, and as well the connection to the package. Then how do you normally use a quartz crystal? If you want to use a quartz crystal, you need to have an additional circuit around it. In 99% of the cases, you would use a Pierce oscillator, which you can see on the left-hand side. So you will have a microcontroller, which will contain the inverter and the above resistor. And additionally, you will need 2 more capacitors and another resistor, and a crystal for sure. What you always need to keep in mind if you're using a Pierce oscillator circuit is that you will have a load capacitance in your circuit. And the load capacitance not just contain your obvious 2 capacitors, so CA and CB, but also all the stray capacitance. So why is this now important? Each crystal which you can buy will have a specific load capacitance, which will just mean they are normally specified for one specific load capacitance. So if the datasheet mentions 20 picofarads, this just means it will work at the optimal point if you have 20 picofarads in your circuit. And to calculate your load capacitance in your circuit, you can use the formula above, which contains CA, CB, and the stray capacitance. Big problem here normally is that you don't know the stray capacitance, because the stray capacitance includes the capacitance of the conductive paths and as well the input and output capacitance of your microcontroller. Sometimes the IC houses mention the input and output capacitance, but not always. So you always guess the stray capacitance normally. So you can say typically it's around 2 picofarads and 7 picofarads, but you will never No, or you can never simulate it. You need to have a final PCB and test it to see if the frequency is within the tolerance. You may ask, okay, why is this important? We're just looking at 2 picofarads or 7 picofarads, which is not really a lot. But for crystals, this can have a big influence. And this could be described by the trim sensitivity. This is just another specification for a crystal, which means how big is the frequency deviation in ppm if you would change the load capacitance in the circuit. And normally if you change the load capacitance by 1 picofarad. As well, you can see you have a formula here which contains C1 and C null, which is just what from the equivalent circuit of the crystal. And you will also include CL, so the load capacitance. So you see this value would also change just because you change the load capacitance. And if you look at a specific crystal or different crystals, you can say the trim sensitivity always depends on the size of the blank. So depending if it's bigger, smaller, which shape it has. The same is for the electrodes. So depending if you have a big electrode or a small one, then like I said, it will vary with the load capacitance, and it would also vary with the frequency. Just because the thinner the blank, you will change the shape again, but for thinner blanks, you will have higher frequencies. So all depends. And then this is maybe a good example. We just measured 2 different parts. So we took a big metal can part 11 by 4.7 millimeters and compared the frequency deviation to a ceramic-based package with 3.2 by 2.5 millimeters. This is just for ideal conditions, and it's just belonging to 2 specific parts. Both parts have 20 megahertz, and both parts were specified at 30 picofarads. Because of this, the frequency deviation at 30 picofarads is ideal, so 0, because we said, okay, we think under ideal conditions, the frequency is exactly 20 megahertz at 30 picofarads. But you can see if you change the load capacitance now in the circuit going upwards and downwards, you will get a frequency deviation. And you can see for the big part, so the metal can part, this frequency deviation will be really high. For example, if we look at 20 picofarads, you can see that for the metal can part, the frequency deviation will be around 25 ppm, but for the metal can part, it could be already 125 ppm. And this will definitely mean this part will be out of spec because crystals are available with 20 ppm tolerance, 50 ppm tolerance, but most of the time not over 100 ppm. So this part can easily be out of spec just because you use the wrong load capacitance in your circuit. And this will happen more easily for bigger parts. For the smaller parts, this effect is smaller, but even here we will see this effect, and even here we could be already out of spec. And this is the reason why I show this, is to show you how important it is to have the right load capacitance. And we will also look at this later because we also will see an effect here if we reduce the size of the crystal. So now we go on to crystal downsizing. So what happens if we reduce the size? Normally there are 2 reasons why we reduce the size. Like I said at the beginning, more and more application gets smaller and smaller, so we just need smaller components. On the other side, sometimes it happens that during the design in, the developer will use bigger parts just because it's easier to handle. You can hand solder them. So just easier to use than like a tiny part with 1.6 by 1.2 millimeters. But then when it goes to mass production, you want to have it as small as possible. So for the design in, they use the big part, and then for the actual part, they will use a smaller part. So, but what is the effect now? What happens when you do this? Therefore, we need to look at the crystal ESR. The crystal ESR is the resistive element of the crystal, which is nearly R1, but it's normally a bit higher than R1. And the ESR will vary with the frequency, the holder type, crystal size, electrode size, mounting structure. And as you can see at the right bottom, we have shown you 3 different parts, 3 different sizes, 3 different electrode sizes, blank sizes. You can easily see, okay, you will not have the same ESR for all the parts. And as a rule of thumb, you can normally say the smaller the part gets, the higher the ESR gets. Yeah. Then normally you can say because the thickness defines the frequency. So if all parts have the same frequency, the thickness of the blank will be the same. But just because the electrode and the blank gets smaller, this will increase the ESR of parts. And if you have a higher ESR, this could have an effect on your negative resistance ratio, which we will look now. So what's the negative resistance ratio or safety factor? In your circuits or in your Pierce oscillator circuit, you will have a specific gain of the amplifier. And this gain needs to be larger than the impedance of the loop. This is the reason why we look at the negative resistance ratio or safety factor, because this defines the ratio between the negative resistance, so the amplifier gain, to the crystal ESR, which represents the impedance of the loop. You could say if both are the same size, so the safety factor is 1, the crystal will oscillate because the gain is equal to the impedance of the loop, and this will guarantee you an oscillation, which is true. But as soon as something changes, as soon as anything varies within your circuit because of temperature changes or any vibrations, it can happen that your oscillator circuit is not working anymore. That's the reason why we say if you want to have a stable oscillation, which can guarantee you the oscillation over any variation within the batch, within the temperature, you should have a safety factor above 5. As I said on the last slide, with smaller crystals, you will have a higher ESR. So if we say the negative resistance normally in the circuit will stay the same, but the ESR will increase, this means that the negative resistance ratio is getting smaller. And it could happen that it could be below 5 and maybe goes close to 1. So this means maybe you cannot guarantee that the circuit will work. So how could you measure the negative resistance, or how can you say, okay, you have a good safety factor? You could just add a potentiometer in series to the crystal, and you increase this potentiometer until the point where the crystal stops oscillating, which is like R at max. And if you add this value to the formula, you can easily say that's your safety factor. And you should have it above 5 normally. That's what we recommend to you. So what can you do if the negative resistance ratio is too small? There's another way to look at the negative resistance in the circuit based on your amplifier, and that is to use this formula. So minus R is the negative resistance, and this depends on the transconductance of the microcontroller, which is normally specified in the datasheet, and the 2 capacitors you use. And you can easily say to improve the gain in the circuit, you have the chance to increase the transconductance in the circuit, which could mean just use another microcontroller, which could be really expensive because you already did all the design for this one. Or you just decrease the capacitors. So you can just use smaller capacitors. You could use another load capacitance in your circuit, and in this way you will improve the gain in your circuit. So this means with a lower load capacitance, you will have a higher negative resistance, which is good because then you will have a higher safety factor. So back to the graph I showed you before. So the black line and the right line will be the same as before. So it's the big metal can part, it's the smaller ceramic part, both specified for 20 megahertz, 30 picofarads. So that's exactly the same as before. But now we compare it to a smaller part with just 2.0 by 1.6 millimeters, also 20 megahertz, but with a lower load capacitance. Because we learned to have a better negative resistance, we should use smaller load capacitance. So in this case, 10 picofarads. That's the gray line. And you can definitely see at 10 picofarads, this part is ideal as before, and the frequency deviation is 0. So better than the red and the black line. But you can also see that going downwards or upwards again, you will change the frequency. And this is not good normally. This effect is smaller than for the others because it's a smaller part. But at the same time, if we go downwards, the effect could be bigger just because a change of 1 picofarad compared to 10 is just bigger than 1 picofarad compared to 30 in the circuit. So it's important to think about this when you say you will just use a smaller crystal with a smaller load capacitance. Because any variation in the stray capacitance or as well changes about temperature, so as well your capacitance value will change during temperature changes. This can cause frequency changes. And the smaller the load capacitance will be, for example, 6 picofarads, 5, it's easily happening that your frequency will change if you just change the load by 1 picofarad because of temperature changes. So always keep this in mind that small load capacitance does not mean everything is working perfect. Then some general design recommendations. In this case, first of all, for the load capacitance, so CA and CB. As mentioned before, you can use this formula to calculate the ideal values for CA and CB if you have chosen a crystal with a specific load capacitance, for example, 10 picofarads. Normally, we would say best is to have CA and CB at the same value. Sometimes this is just not working because not all the capacitance values are available for the capacitors. So sometimes it's easier to have some different values. In this case, we always recommend it should be that CB is bigger than CA. Moreover, we recommend that CL should not be smaller than 2 times C null, which was the shunt capacitance for the crystal. This is just because you say if you have smaller CL, the frequency will easily vary with if you have any frequency load capacitance deviations. So 1 picofarad change will cause a big frequency change. And then again, the stray capacitance you will never know because you cannot simulate it, but typically it's between 2 picofarads and 7 picofarads. Then we move on to design recommendations for RS. That's the additional resistor you normally have in your circuit. This is just used to reduce the power over the crystal, so protecting the crystal to overdrive. This is important, especially for smaller parts, because normally they have a smaller drive level. Then it also isolates the output driver from the complex impedance of the crystal and CA of the crystal and CA and CB. Additionally, it forms a low-pass filter together with CB, which will just force the crystal to oscillate at fundamental mode. You may know that crystals could also oscillate at an overtone mode, so at a third overtone or fifth overtone. And to avoid this, you can use this low pass filter function just to make sure that the crystal oscillates in his fundamental mode, so at the right frequency. And we said RS is definitely needed for lower frequencies below 8 megahertz, just to have an additional phase shift and to guarantee that you have 360 degrees phase shift in the network in total. And as well, this phase shift in this case will reduce the jitter and the phase noise behavior. But we also say, okay, if you use a crystal above 20 megahertz, this function is normally not necessary, just because you have enough phase shift in your circuit. And to have the ideal value for RS, we normally recommend to say that RS should be equal to the impedance of the capacitor CB. Then the drive level, which was mentioned before shortly. So the drive level just specifies the power dissipated at the crystal. If the drive level is too high, you can get damage of the crystal, just because you will have a mechanical oscillation of the crystal, and if the power is too high, this can cause even the break of the crystal blank, so it will not work anymore. On the other hand, if the drive level is too low, this could mean that the crystal does not start up and will not oscillate. The drive level is always specified in the datasheet as a maximum value, so you will know which value you should use. Most of the time also a typical value is mentioned. And you can measure the drive level in your circuit. Therefore, you just need to measure the current flowing over the crystal. You need to know the ESR, which is specified in the datasheet, or you can just measure it, which is R1 and the additional calculation. And if you just do all together, you will get the drive level. And with this calculation, you can check, okay, is the drive level in your circuit too high? Is it possible that you damage the crystal, or is everything working fine? So that was some general recommendation. Now we just sum up which problems you will get with using smaller crystals. So your plan is to design or redesign the circuit with a smaller crystal. First thing that comes to your mind now is saying, okay, smaller crystal will have a higher ESR. This will just means you have a lower safety factor. From this, it follows that maybe your oscillation is not stable now. Then you think, okay, what can you do here? Easiest way is now to reduce the load capacitance in your circuit. But keep in mind, it could happen as well that your frequency will change then. If you change the load capacitance and reduced it, the negative resistance will increase again. This will help with your safety factor, which will increase as well. And you're happy again, your oscillation is stable again, and everything works fine. So that's the short summary of what we just discussed in the last 30 minutes. Thank you for listening to this presentation, and just ask any questions you have.
Yes, thank you, Sarah, for your interesting presentation. As you already mentioned, now we would like to turn our attention to your questions, and we will wait a second until some questions will come in. You can enter your questions in the chat function in the webinar control panel. So let's take a look at the first question, Sarah. How do you measure the current over the crystal for the drive level calculation?
So how can you measure the current? Normally, the easiest way is just to use a current probe. Yes, it's true, you will change the load capacitance because the current probe will have a specific capacitance value, but at this moment, you just wanted to know the current. It doesn't matter if the frequency is a bit out of spec, just important is at this measurement, the current. So in this case, the easiest way for you is just to measure the current with a current probe in series to the crystal.
Okay, thanks, Sarah. And another question, how can you reduce the stray capacitance on your PCB?
As well, here the easiest thing is always just to start with using small spaces between crystal and microprocessor. So just have short lines, short ways, not long lines. Then as well, don't have 90-degree bends. So typical what you also do normally. Then to avoid any other signal lines around it, just to make sure you also don't have any jitter or phase noise impacts. But first of all, always start with short lines.
Okay, thanks, Sarah. Another question is, do all these rules and recommendations also apply to watch crystals?
Yeah, all these rules also apply for watch crystals. So as you all know, watch crystals are a specific kind of crystals with 32.768 kilohertz. So a really low frequency. In this case, all the rules I just explained also need to be considered. And most important is to have the additional resistor RS to reduce the drive level. Because watch crystals really have a really low drive level compared to megahertz crystals, and you always need this resistor to make sure that your crystal is not overdriving.
Perfect. Thanks, Sarah, for your explanations. I would say if there are any questions left, we will answer them via email afterwards. But for now, we are finished with this presentation. Thank you very much, Sarah, and thank you very much for your attention. I hope you enjoyed our presentation. The next presentation topic is frequency products, quartz and oscillators, introduction of new products. And this presentation will start at 5 p.m. See you there and enjoy our digital days. Goodbye and thank you.